months, and they're going to tell you how they're going to help them solve that problem.
Hello and welcome, ladies and gentlemen, to our senior project. I'm Herrmann, Industrial Supervision Major.
And I'm Mahrenholz, I'm an Advanced Manufacturing Major.
Our senior project is a plan to cool non-contact water basin at Abengoa Bioenergy Plant, Mount Vernon, Indiana. Abengoa is a Spanish international corporation. They deal with biotechnology that specializes in biofuels, and they research sustainable technologies and implement them into their processes. They currently work with solar power, second generation biofuels, and desalinization. Divisions within Abengoa is the acquisition of raw materials, the bioethanol origination, the production of the biofuels, marketing of bioethanol, distillers of grain with soluble and sugar, cogeneration, and new technologies. Abengoa was founded in Sevilla, Spain, and that is where it is headquartered. It's also on 3 continents, including North America, South America, and Europe. They have 9 plants in the United States and 11 internationally. The plant in Mount Vernon, they deal with denatured alcohol that they use for the bioethanol. They also produce corn oil. They deal with dried distillers grain soluble, wet distillers grain was soluble, and distillers soluble. The problem that we ran into, that Abengoa is running into, is they use non-contact water to cool processes throughout their plant. This water does not come into contact with any agents or anything else. It's just straight water used to cool the plant. This water is collected into a basin, and the problem is that the water, when they use to cool the processes, is heated up to, on average, about 90 degrees Fahrenheit. The water is then eventually returned back into the Ohio River, and the problem with Abengoa is that the Indiana Department of Environmental Management and the Environmental Protection Agency standards are not being met by the water being returned back to the Ohio River. The environmental impact of this process is that the hot water is introduced into the cold environment that then promotes algae growth in the bottom of the rivers, and also will pull the oxygen out and kill off the fish and other animals living in the water. The IDM standards for the months that are in question is in December, which is 57 degrees. It's a standard. In January and February it's 50 degrees, and in March it's 60 degrees. These standards also have a 3-degree variance in them, so there's a very wide range that the water needs to be cooled down before it goes back into the environment. And now Matt will go over the plant layout and design possibilities.
This is the aerial view of Abengoa Bioenergy. You've got the creek that runs to the river, and then right here you've got the drainage ditch that runs to that creek where a lot of the cooling is taking place currently. And then this is the energy center where the non-contact basin is currently right now, where our design will be held. The current layout is just a simple 3,000 gallon basin. There are 3 main parts that run into that. You've got your RO blowdown, which is reverse osmosis. You've got your boiler blowdowns, and you've got your cooling tower blowdowns. At a certain level, it gets put to a certain level, and then you've got these 2 pumps that pump it out underground to a certain valve that then takes it to whether it goes above ground or below ground, depending on your seasons. The peak flow processes are, you got your boiler blowdowns at 50 gallons per minute. The RO2 blowdown reject is at 333 gallons per minute. The cooling tower bleed offs are at 262 gallons per minute. And then the peak flow rate out of the basin is at 848 gallons per minute. Also, the water coming to the plant from the well at about 55 degrees is roughly just under 2,200 gallons per minute. The drainage ditch, like I said before, it's just for cooling. It's rock line. It's got a erosion control liner under that. They use different dikes and dams for cascading. Currently it takes 10-minute travel time. They've got a 5-degree drop from their out temperature. we had two designs. Our first design, we were going to use a 500 gallon per minute plate frame heat exchanger with 90% efficiency. We're also going to use a 500 gallon per minute pump. And currently in that energy center, they've got a brine tank that we're going to convert to a holding tank to help water cool down what it is. It's going to recirculate and get that water down to a more manageable temperature for our non-contact ditch to cool it down the rest of the way to the EPA and IDIC standards. This is a AutoCAD layout. It's just a flow diagram. You've got your well water coming in here. You've got, that runs up, it's pumped up to this heat exchanger. And then you've got, from one of the pumps that it's got running over the brine tank. This tank's going to fill up, and it's going to run through this. It's going to be the water pump. And then after the water pump, it goes to the heat exchanger. You're going to get 90-degree water and about 55-degree water. You're going to have the heat exchange. And then it's going to go back into the brine pump or the brine tank with recirculation. It's going to take about a 15-minute residence time to cool that down to as close as we can get to about 60 degrees. And then we're going to take the water in the brine tank and pump it back out into the piping below. The advantages for this design, it's more consistent cooling. It's not dependent on the ambient air. It's easy maintenance on the components. It's higher efficiency. And the 15-minute residence time, like I said before, allows more time for the cooling to take place. The disadvantage is that you've got more pipe you have to weigh to be diameter. The second design consists of a 500 gallon per minute tube and shell heat exchanger. It's an air to water, 2,000 cubic foot per minute radial axle fan. And then another main component for that's just your controls and your drives for the fan. The CAD layout is we've just got our radial fan pumping, bringing in ambient air to the tube and shell heat exchanger. It's cross exchanging with the well water. And we're going to take that chilled air and run it directly into the piping to where it discharges out of the basin. The advantages is it's cheaper than the do-nothing approach, and it's also easy maintenance. There's less really to have go wrong with that design. The disadvantages, though, it's dependent on the temperature and the ambient air temperature. You know, living in Evansville recently, you've got days where it's 60 degrees, and the next day it's 20 degrees, and there's snow on the ground. You also have issues with the fan motors and bearings. It's higher costs and possibility of clogged airlines. Recently, we've been doing some drainage ditch modifications. We added in, we made our dams a little bit taller, a little bit wider because the issues we were having with it, they were falling over due to the hydraulic pressure of the water. We also added more cascades of gravel and river rock, and we got the time from 10 minutes to an 18-minute residence time and a degree or a temperature difference from 5 degrees to 12.5 degrees on average. These are just some extra modifications we made. This one is just a single wide, single high dam, just filled in with rock. And we use that just as an aeration to get that water cooled down. And then the second modification we've got is the last dam before it drops or drains back into the ditch. And what that does is it just collects everything in cascades to get the most aeration you can possibly get out of it. I'm going to send it back to Adam. He's going to talk to you more about the financial aspects.
On the cost of design one, as you can see, the grand total is just under $60,000. We've got our quotes from Alpha Laval for the plate and frame heat exchanger. The water pump came from Xylene Water Solutions, and then the brine tank modifications came from WYN Industries, and then all that, and then plus the pipe and the valves and all the couplings came from the 2007 Means Construction Guide. And with that, we had to use a location factor into Evansville that just took the national average across the board, and so that's where the .916 comes from. And then also, since the guide is in 2007, we had to do an inflation factor to get it up to 2013 prices, which was 12.6%, and that got us to our total of just under $60,000. Cost of design two, as you can see, is just under $92,000, and we got all the quotes on this came from the Means 2007 construction guide. We still had to allow for the same location factors and the inflation cost, and then also labor costs and everything in there. And then the do nothing approach, which is It's just Abengoa standing pat, doing nothing, and what we've already done with them. For the scenario, we took that they had a fine a month for 4 months, and that got us up to $100,000 because the max fines for it is $25,000. They are tested. The water temperature is tested twice a week. So, as you can see at the bottom of the screen, the $800,000. That is where that comes from, because they've been tested and fined twice a week for the 4 months, which would the max fines would get you to $800,000. The economic decisions came down to design one as a payback in less than 3 months versus the do nothing plan. It was also cheaper than option 2 by about $32,000. The design 2 had a payback period of 4 months versus the do nothing plan, and obviously the do nothing plan was the most expensive one. So our final decision is, with the reasons we've stated and the costs, option 1 is the best design that Abengoa should use going forward.
And then references, we had Jason Veers, he's the plant engineer at Abengoa. Timothy Weimer, he's the QSC manager as well at Abengoa. We had Dave Ellert, and then the Means 2007 construction guy. Our acknowledgements, Professor Sprouse, Dr. Mitchell, we had Dave Ellert, Don Moore, Tim Weimer, Daryl Sanford, he's the plant manager out at ADI, and Jason Beers again as well. This concludes our presentation. You guys have any questions?
Is there a reason why you didn't consider like a geothermal design, like just essentially burying the pipes?
Well, whenever we were talking, it was something I considered, but the way the layout of the plant is right now, there's not much room to really do any excavation, and the amount you'd have to do for it, with the velocities and flow rates you'd have to have, it would be a monumental task and it'd be very, very expensive.
Any other questions?
Okay, thank you.